So in this video we are going to discuss some new topics. Firstly, we will talk about enthalpy. Symbol is H. So this enthalpy simply means heat absorbed at constant pressure. So in the previous video we got a relation, okay, at constant volume, okay, heat absorbed at constant volume. Okay, I'm writing in short form. We got delta U, okay, change in internal energy is equal to QV. So this V means constant volume, okay. So heat absorbed at constant volume, okay, is equal to change in internal energy, okay. So let's take it as equation 1, okay. Now heat absorbed at constant pressure, I'm writing in short form, can be written as delta U, okay, QP, okay, and P delta V. So this QP is heat absorbed, okay, denotes heat absorbed at constant pressure, okay, by the system, and minus P delta V represents, okay, represent work done by the system. So since the system is doing the work, okay, minus sign comes here, okay. Now let's say there are initial and final state, okay. So initial U2, U1 and U2, initial, final, okay, let's denote it by the initial as U1, final as U2, okay, and initial volume V1, V2. So in this case, okay, we can write this above expression, okay, as U2 minus U1. So U2 minus U1 will give you change in internal energy, QP P. So this delta V will be simply V2 minus V1. Now let's rearrange this equation, okay, rearranging the above equation, okay, let's take QP outside, heat, okay, outside, U2 plus PV2 minus U1 plus PV1. So we have arranged this one, okay. Now let's take this one as equation 2. Now there is another thermodynamics, okay, term known as enthalpy, okay, which is H, okay. So enthalpy, there is a formula, H is equal to U plus PV, okay. This means heat content, okay, or warmth. Now this equation 2, okay, we can rearrange this one and can be written as QP is equal to H2 minus H1. This will be simply equal to delta H, okay. H2 minus H1 will be delta H, okay. That means enthalpy, change in enthalpy. So how this H2 and H1 came is, you see this one, U plus PV is equal to H, okay. So U2 plus PV2, that means this will be H2. U1 plus PV1, that means it will be H1. So simply we write H2 minus H1 gives this one. Now, okay, this heat depends on the path, okay, heat flow of heat from one point to another point. It depends on the path, okay. But this H, okay, is a state function. This enthalpy is a state function because internal energy, okay, is a state function. Even pressure and volume, they are state function. That's why this one is a state function. Enthalpy is a state function. Now for finite change, okay, changes at constant pressure, okay. So if there are finite changes at constant pressure, we can write this equation. Let's take it as equation. We can write this equation as delta H is equal to delta U plus delta PV. Now in this case, it takes place at constant pressure, so we can write this equation as delta H is equal to delta U plus P delta V, okay. Now suppose, okay, if the reaction, okay, is exothermic, that means heat is released, okay. That means delta H will be negative, okay. And endothermic will be opposite, so delta H will be positive, okay. So please remember this one, okay. Now let's discuss another one, okay. So in this case, we will consider gases, okay. So a reaction involving gases, okay. So the first gases, okay, let's the total volume of the first gas be VA, okay. And the volume in the product, okay, let's this be reactant product, okay. Volume of the reactant of gas as VA, and volume of the gases in the product VB, okay. Let's take the NA, okay, be the number of moles of gaseous reactants, okay. Gaseous reactant, number of moles of gaseous reactants, and NB, numbers of moles of gaseous product, okay. So let's take another condition, okay. So this takes place at constant pressure and temperature, okay. I'm writing in short form. Now you all know the ideal gas equation. The ideal gas equation is PV is equal to nRT. So for this case, okay, for these gases, we are going to write it as PVA is equal to NART, and this is for the product. And now, sorry, reactant. Now for the product, PVB and BRT. So this can be rearranged into PVB minus PVA is equal to NBRT minus NART, or we can write it as, we can take common, okay, P common here, VB minus VA. In this case we can take RT common, okay, and NB minus NA inside the bracket. So VB minus VA it will simply give you delta V, okay, change in volume. Now NB minus NA, okay, change in the number of moles of gaseous, reactant and product. Okay, so this will be the change in the number of moles of gaseous, reactant and product. So let's denote it by delta NGRT. Okay, the change of this gaseous moles of reactant and product, let's denote it by this one. Okay, now we know that, okay, I'm writing in short form. We know that delta H is equal to delta U plus P delta V. Okay, we got this one, okay, from our previous discussion. Let's take this one as 1, okay, equation 1, and this one as equation 2. So substituting this value in equation 2, what we will get is delta H is equal to delta U. Okay, so this P delta V is equal to this one. Okay, so simply we write this one down here. Okay, delta NGRT. So with this relation we can calculate delta H or delta U. That means change in enthalpy or change in internal energy, we can calculate using this relation. Let's see one problem. Okay, problem 6.5. If water vapor is assumed to be a perfect gas, molar enthalpy change for vaporization of 1 mole of water at 1 bar and 100 degrees Celsius is 41 kilojoule per mole. Calculate the internal energy change when 1 mole of water is vaporized at 1 bar pressure and 100 degrees Celsius. So in this case we are going to calculate the internal energy. Okay, that means we are going to calculate delta U. We have to find this one, delta U. Okay, in this case internal energy. Okay, so we have to calculate internal energy, okay, of this one when this 1 mole of water, okay, is vaporized at 1 pressure. Okay, now solution. So what is given? 1 mole, so N is equal to 1. Okay, pressure is given 1 bar. Now temperature is given 100 degrees Celsius. Okay, so while calculating we have to convert this degrees Celsius to Kelvin. Okay, so I think you have studied about this conversion in unit 1. Okay, now how do we convert this Kelvin? Okay, degree to Kelvin. Okay, Celsius plus 273. Okay, so Celsius plus 273 will give you Kelvin. Okay, so simply 100 degrees Celsius will give 373 Kelvin. So in this case we convert this one to 373 Kelvin. Okay, so temperature will be 373 Kelvin. Now enthalpy is given. Okay, this molar enthalpy is 41 kilojoule per mole. So delta H is 41 kilojoule per mole. Now the reaction involved is H2O liquid into gas. Okay, so we know that formula we just got. Enthalpy is equal to, change in enthalpy is equal to delta U plus delta NG RT. So we have to find this one, so we'll just write this one, delta U is equal to delta H minus NG RT. So we are going to put these values here. Okay, so delta H 41 kilojoule mole inverse, and N we got this one as 1 into this R. Okay, it's a gas constant, so its value is 8.314. okay, but we are just writing 8.3 here, joule mole kilo inverse per mole per kilo. Okay, into temperature, this one 373 Kelvin. So what you will get is 41 kilojoule mole. So you multiply these two, so you will get 3096 joule mole inverse. This Kelvin you can cancel, minus k minus 1 and k you can cancel. Okay, so you will left with J joule mole. Okay, inverse. Now we are going to convert this joule into kilojoule, same as this one. So if you divide this by 1000, you will get this one as 3.096 kilojoule mole inverse. So 41 kilojoule mole inverse. So your answer will be 37.904 kilojoule mole inverse. Next topic is extensive and intensive properties. So extensive properties. Extensive properties are those properties whose their value depends on the quantity or size of the matter. Okay, how much quantity is present and how bigger the size. Okay, it will depend on that. Okay, those quantities. So example are mass, volume, internal energy, heat capacity, entropy, etc. This mass, it will depend on the quantity also. Okay, how much quantity is present. Okay, and this mass, okay, suppose the mass of 1 kg of book, okay, one book or textbook. Okay, if you add one more book, it will increase. Okay, like that. Okay, or 1 mass, okay, 1 kg mass of sugar. Okay, if you add one more kg, it will increase to 2 kg. So mass, it depends on the quantity or size. Okay, volume also, it depends on the quantity or size. Okay, so volume of water, okay, 10 liter of water, and then if you add 5 more liter, it will become 15 liter. Okay, so volume increases. Okay, or if we reduce, okay, if we take out 5 liter from that 15, it will become 10 liter. Okay, so it will depend on the size or the quantity. Internal energy also, this total energy. Okay, this will also depend on the quantity. Okay, the quantity or size of the matter increases. Okay, it will affect the internal energy. Okay, heat capacity. Okay, we'll discuss a little bit about heat capacity in the next topic also. Okay, so it will also depend, okay, on the quantity. Okay, amount. So how much heat is applied, okay, will depend on that. Entropy, measure randomness. Okay, degree of randomness. Okay, more gaseous molecules, more randomness. Okay, and less gaseous molecule, less this randomness will depend on the number of molecules. Now the next one is intensive property. These properties do not depend on the quantity or size of the matter. Okay, that means they are independent. We can say independent. Okay, they do not depend on this quantity or size. Okay, example is temperature. So the temperature, okay, of this room is constant. Okay, the temperature at this point here will be same. If I move here also, at this point the temperature will be same. Okay, from this point to this point also it will be same. Okay, or the temperature in a box. Okay, this box, okay, in a box will be same. Okay, even though we make a partition, okay, here also in the middle. Okay, so in this box temperature will be same. Okay, so it does not depend on the size, okay, or quantity. Density also will not depend on the size. Okay, so suppose the density of water, okay, in this beaker, okay, will remain same. Okay, even if we take small amount of water, okay, density will remain same. Okay, so this density you will get by, if you divide mass by volume, you will get the density. Now pressure, okay, pressure also will be same. Okay, does not depend on the size, okay, or matter. So another one is concentration. Okay, concentration. So this concentration will not depend on the quantity or size. Okay, like molarity, normality, all those. Okay, so molarity of 1 molarity of NaCl, okay, will be same. Okay, 1 molar of NaCl, okay, in water. Okay, so this NaCl, 1 mole of this NaCl will be same. Okay, even if you take a spoonful of this NaCl solution, okay, that spoonful solution of NaCl will be 1 molar only. In the same way, normality, all those, okay, will be same. Okay, even if the amount, okay, even if we take 1 molar of NaCl or 1 normal, all those, okay, of those solution, like sodium hydroxide, okay, 1 normal sodium hydroxide, okay, even if we take this one, so suppose this is in liter, okay, if we take 100 ml also, this will remain 1 normal. Okay, 1 normal or 0.1 normal. So if we take in 100 ml also, it will remain 0.1 normal, and that means it does not depend on the quantity or size. So another shortcut method is, if you divide two extensive, okay, property, extensive, you will get intensive property. Okay, so example will be density. Okay, density, mass is also extensive. Okay, volume is also extensive. So if you divide, you are getting density. This density will be independent of this mass or volume. Okay, this density value will be independent, so you get intensive property. Okay, molar mass divided by number of moles. Okay, so this one is extensive. Okay, this is the number of moles. So if you divide this extensive property by a specific number, what you get is intensive property. Okay.